Hi, we are on unit number 2. No, excuse me, unit number 4, working through Newton's laws of motion, and in this particular video we're going to work through Newton's first law of motion. In a previous in a previous uh, in a previous video we talked about balanced and unbalanced forces, and we found out that balanced forces do not cause any kind of acceleration, so the I guess best way of saying it would be the object will not be speeding up, it will not be slowing down, and it will not be turning. If the forces acting on the object are unbalanced, then we'll have an acceleration. The object will either be speeding up, it'll be slowing down, or it'll be turning. And all that's kind of important as we begin Newton's first law of motion. So let's start out. We'll start with the definition, and then we'll run through the fact that Newton's law has two parts. So here's the definition, and then we'll kind of, I guess, break up Newton's first law of motion into two pieces. Part number one, and then part number 2. Now there are quite a few videos and cartoons, and on this particular video that I'm system or program that I'm using, I really can't show those videos or those cartoons. It doesn't necessarily work that way. So, but I do have at least two demonstrations that I'll do for you, and you get a feel for it that way. Okay, so Newton's first law of motion, here it is. Number 1, it is the resistance of an object to change its motion. When you, I don't know, I guess you could think of some of you who are stubborn. So if anybody has ever called you, you're stubborn, then you would say, well, then I must have a lot of resistance to change, which means whatever I'm doing, I just don't want to stop doing it. And so when we talk about Newton's first law of motion, we want to talk about this idea of resistance to change. Whatever it's doing, it always wants to continue to do that. We give that whole concept a name, and it's called inertia. An object, let's see, inertia, I'm ahead of myself. So inertia is the resistance of an object to change its motion. So when you hear Newton's first law of motion, you want to think of inertia. And when you think of inertia, you want to think of Newton's first law of motion. Those two mean the same thing. And Newton's first law of motion has two parts, and those two parts I'm sure you've already heard of. And so let's go through and define those. So here's the first part. An object at rest tends to stay at rest until an external, unbalanced force acts on it. So an object at rest tends to stay at rest unless you do something to it. You push it or pull it, and those pushes or pulls are unbalanced. Couple examples of that. I remember that when I would come home from school, I would walk in the door, and I would throw my bag on the floor, which would upset my mother. And then I would walk over to the sofa. I would plop myself in the sofa, put the remote control in my hand, and surf. And my mom, she would not like that, because she knew that at that point in time I had a whole lot of inertia, which means an object at rest tends to stay at rest. And baby, once my butt hit that sofa, I wasn't going anywhere. It'd probably take food and a meal to get me out of that sofa, and that kind of drove her crazy. And I guess I can understand that. But an object at rest tends to stay at rest. So next bullet point, what is the acceleration of an object when there is no external force? Well, if you're at rest and you're going to stay at rest, then there's no acceleration. So the acceleration is 0 meters per second squared. All right, the next one. Inertia always resists changes in velocity. So when you think of inertia, you resist changes in velocity. So you resist speeding up, you resist slowing down, and you resist turns. If I'm at rest, I don't want to speed up. I just want to stay at rest. So inertia is always resisting what you're already doing. It's resisting any kind of change to what you're already doing. If you're at rest, you want to stay at rest. Anytime we resist a change in velocity, we call that change in velocity an acceleration. So inertia means, if you have inertia, it means you want to resist an acceleration. You don't want to speed up, you don't want to slow down, and you don't want to turn. An object at rest tends to stay at rest. Alright, so I've got one example that I think I can do on a video here. And so I'll come up here, see if I can zoom out a little bit. And what I have is I have a card and a beaker. And we'll put the card on top of the beaker. And then I have a coin, my life's savings. And so what I'm going to do is this. So I've got kind of like that. You can kind of see it that way. And I'm going to come across, and I'm going to go ahead and flick the card. And when I flick the card, the coin here, has inertia. If it has inertia, it wants to stay at rest. So even though the card's going to move sideways, if the coin has enough inertia, it'll stay there too and fall into the beaker. And boy, that was a horrible example. I didn't push that enough. How about we try it again? There we go. And so an object at rest tends to stay at rest, and that coin then stayed right there. So the card on the second one, I guess the second attempt at it, so the card went flying out, and the coin just stood right there, and then gravity pulled it into the beaker. An object at rest tends to stay at rest. Some other examples similar to that. So if you wanted to maybe write those on the side over here, let's see if I can pull this out. I'll write those. Some other examples would be tablecloth. And actually in class, I'll set up dishes on a tablecloth, kind of similar to the card and the coin, and I'll pull the tablecloth out from underneath the dishes, and the dishes will stay right there. An object at rest tends to stay at rest. A couple other examples. I gotta yawn. Whew. All right, a couple of examples are like a punching bag. I remember watching all the Rocky movies, and when Rocky would be in the gym training, there would be that big punching bag, not the small teardrop one that was always over his head, but the big one, and Rocky would be hitting the punching bag and hitting the punching bag, and the trainer, I always found this interesting. The trainer, who's usually some old scrawny old guy, would be standing right behind the bag. And well, that's interesting. Rocky can hit that bag as hard as he possibly can. And even though the trainer is basically up against the other end of that bag, he's perfectly fine. But if that bag were to miraculously disappear while Rocky hit that bag, and then Rocky's punch continued through and hit the trainer in the mouth, probably the last thing that trainer ever does. So what's the difference? Why is it that the punching bag kind of protects the trainer? Well, those punching bags, if you ever have tried to push them around a little bit, are incredibly heavy. There's a lot of mass there. And so if it has a lot of mass, that means it has a lot of inertia. If it has a lot of inertia, that means it wants to stay at rest. So even though Rocky comes in and hits that bag basically stays at rest. And if it stays at rest, it won't move into and clobber the coach, and the coach will be just fine. Another one, and I can maybe kind of use this as an example. Sometimes when you're eating your cereal, so let's pretend this is a bowl here. You're eating your cereal, maybe your alphabet cereal, and so you got all your alphabets here, and there's an O on the other side over there of the bowl. And you say, well, I like to eat that O over there. So what you do is you take your bowl and you rotate your bowl of cereal. But as you rotate your bowl of cereal, that O stays right there. It doesn't rotate with the bowl. You're like, what's going on? Well, what's going on is that object, that O there, is at rest, and it wants to stay at rest. So as you try to rotate the bowl, the O says, I don't want to rotate, and it stays right there. Kind of similar to like when you're in the summertime and you have a glass full of ice water, and you go up and you try to drink that ice water, and that ice gets all over your lips. You say, I'd like to drink from the other side of that glass, and so you rotate the glass, and the ice doesn't rotate with it because the ice is at rest and wants to stay at rest. So that's another example, and there are others that we'll talk about in class. Kind of tough, kind of difficult to do on video here. All right, the next one, part 2. So this is all the second part of inertia. So this would be an object in motion, tends to stay in motion in a straight line. All right, so you probably heard of that before. An object in motion tends to stay in motion. So if it's in motion, whatever it's doing, it wants to continue to do that. Well, what does that motion look like? Well, it'll stay in a straight line, and it'll move in that straight without speeding up or slowing down until an external balance force acts on it. An object in motion tends to stay in motion until in a straight line without speeding up or slowing down until an external unbalanced force acts on it. What are some examples of that? I'll do those examples and then we'll fill in the rest of these blanks real quick. Some examples of that. Right here I have a hockey puck. I'm going to zoom out a little bit. I have a hockey puck, and it's actually not a real hockey puck, but one that is kind of designed for this particular experiment. And you can see there's a hole at the bottom of this. And then on the other side we have kind of like a rubber stopper that has a hole in it as well. And that hole goes all the way through. So if I put this on top of here, can you see the white paper underneath? That doesn't work that well. All right, what I have is a balloon. I'm going to blow the balloon up. I'm going to take the balloon and put it on top of the stopper. And if I put it on top of the stopper, then the balloon, you can kind of see it here, the balloon, as the balloon exhales, it's going to let air through, and you can hear the air there, air through that hole, and it produces a cushion. And so that puck can kind of move freely on the ground. And my balloon fell off, so let me try it one more time. And see if we can push it on here. And see how this works. And there it is there. So it kind of glides on a cushion of air. An object in motion tends to stay in motion until an external unbalanced force acts on it. And there's the unbalanced force. A little bit of friction against the table was that unbalanced force, and it caused it to slow down. And we're going to go to that real quick. So let me zoom in. So let's see if we can unpack this definition a little bit. So an object in motion tends to stay in motion. We know that. At A, now let's see, instead of saying in a straight line without speeding up or slowing down, is there another way we can kind of maybe state that? So if we're not, let's see, if we're moving in a straight line, we're not speeding up and slowing down, and we're not turning, what does all of that mean? It would mean at a constant velocity until an external unbalanced force acts on it. So instead of saying, let's see, up here, straight line without speeding up or slowing down, we could just say constant velocity, because that's what that means. Let's see the next one. An object in motion tends to stay in motion without, well, what does constant velocity mean? If I'm moving at a constant velocity, then I am not accelerating. So I've kind of shortened that up a little bit. An object in motion tends to stay in motion without accelerating until an external unbalanced force acts on it. And like I said earlier, I do all these in class. I'll do all these DVDs with you and go through all the cartoons, and some of them are very, very good. Okay, key concepts. One word that sums up Newton's first law of motion. We did that already. And that's inertia. So when you hear about inertia, think of Newton's first law of motion. Newton's first law of motion, both parts, describes the motion of an object when the forces acting on the object are balanced. So an object will, if it's at rest, it'll stay at rest until the forces are unbalanced, or while the forces are balanced. An object will, if it's in motion, will stay in motion in a straight line without speeding up or slowing down, as long as all the forces are balanced. If they're unbalanced, then we get an acceleration. And that's what we're going to talk about right here. So unbalanced forces cause accelerations or changes in velocity. Balanced forces cause no changes in motion. So whatever it's doing, it just keeps on doing that with no changes at all. And then the last one, no force is required to keep an object at rest. So if I have a beaker right here, I don't need to do anything to keep that beaker right there. It'll stay right there. I don't have to cheer it on, write it notes to stay at rest. It'll stay at rest on its own. Same thing. No force is also required to keep an object in motion. If an object is in motion, it'll stay in motion. Just as much as if it's at rest, it'll stay at rest. If it's in motion, it'll stay in motion with the same desire. No difference there. All right, on the next video, we'll start with Newton's second law of motion.